I am Oh Yangzhong, the presenter of this week, and our team members are Jiang Xianzai, Xiao Nan, Liu Bingnan, Cao Shangfei. This week, we will introduce the steel structure of Beijing Stadium. The content is foundations and twisted element, challenge, and superstructure.
Henry Zhang of the National Stadium wastes no time and assembles thousands of workers. The construction accelerates.
We put in 7,000 people working around the clock in 3 shifts a day.
The crew must force the concrete to defy gravity. It needs to be pumped up from the bottom of the forms through reinforced steel beams which strengthen the concrete. But the thick wires are slowing them down, and they still have 4 floors left to go. With less than 6 months before winter, hundreds of tons of concrete must be poured at the site.
First, look at the foundation. All vertical load-bearing elements are supported on the reinforced concrete pile caps supported by cast in-situ concrete board piles with a diameter between 800 mm and 1000 mm, founded in the cobble/gravel straightened layer, about 38 meters below existing ground. A plinth with a 1-story basement surrounds the concrete bore area, resting on a shallow pad foundation on the natural subgrade at about 8.5 meters below existing ground. Then we look at the structure of all the geometrical conditions within the stadium. This box section was defined using a control surface that was part of the structural envelope. The outer flank of the box always remains parallel to the control surface, resulting in a twisting, curving box section that changes as the element progresses along the surface of the structure. The way the geometry was defined resulted in even the most twisted element being forming from developable surfaces. This means that the individual surfaces forming the box sections could be flattened out and cut from a flat steel plate, and then rolled to form the fabricated box section. The very long 3,030 meter span caused the seismic design to be significantly different in several ways from that of typical tall buildings. For instance, limiting interstory drifts and the detailing for ductility were insufficient for the bird's nest roof structure. It could have collapsed straight downwards without lateral sway, due to damage to its gravity force resisting system from vertical earthquake ground shaking alone. The long span also causes the strength capacity of the primary truss members to be taken up primarily by gravity loads. The box section top chord and diagonal members in the primary trusses are subject to high axial compression forces under gravity loads, and will sustain damage and degrade the strength due to global as well as local buckling. Ductile detailing measures for the bracing members in special concentrically braced frames were thus insufficient to prevent collapse of the roof. It was necessary to limit the post-buckling axial shortening of the top chords and the compression diagonals of the primary trusses, thereby limiting degradation of compressive strength. The bowl is split into 6 segments with 200 mm wide movement joints between them. Each segment forms an independent structure with its own stability system provided by column beam frame action, and a concrete staircase and lift course. The 6 segments are between 120 meters and 150 meters long. The movement joints that separate them are continuous through every floor of the bowl, including the terracing. The lower ground level is of 500 mm thick flat slab construction, acting as a floor diaphragm to tie together the foundations. The slab thickness changes due to the increasing span caused by the tapering of these grid lines. And next week, we will introduce the roof technology of Beijing Stadium. Thanks for watching.